Yesterday, Commission President von der Leyen spoke in front of Hydrogen Council and said, hydrogen is a key asset for European Green Deal. Monday, I read a blog from IEA Executive Director Fatih Birol saying, well, the task is to move from 450,000 low carbon hydrogen production now to 40 million tons by 2030. And that leads us very close to what the discussion we had already last year. And Keith was there, Ronnie was there, and Christopher, where we looked on hydrogen technologies. And what we would like today ask, what happened after a year? There have been immense development on politics, but what happened with technological developments? And for this, we have an excellent panel. We have Barbara Jinks from IRENA. We have Kees van der Leuen from Guidehouse. We have Ronnie Belmans from Energiewil and Leuven University. And during the seminar, Yorgos Chatzimarkakis will join us also to participate in the debate. And now for introducing the debate, I give the floor to Christopher Jones, that we will moderate this event together. Christopher.
Many thanks, Andreas. I'd just like to try and frame the debate today. And as Andreas said, thank you very much indeed, everybody, for joining. Because we'd like to take a slightly different approach to the issue today. Because there's a lot of events on hydrogen, quite rightly, at the moment. And ask the question, where are we today and where are we going? Because we're at kind of a staging post in terms of the development of the regulatory framework in terms of hydrogen between the time that this debate really started in earnest and when the Commission is going to make its concrete proposals in October of this year, and at the same time as member states are turning their hydrogen strategies where they exist into concrete support mechanisms in the light of the European Recovery Plan. So we'd like to ask three questions, which is what do we know today about hydrogen? What are the things we do know about hydrogen and hydrogen markets tomorrow? But more importantly, what don't we know? What don't we know about hydrogen markets and where they're going to go in future? And third, so you can take a third issue from there, which is what additional things do we need to know at the EU level, does the Commission need to know, if you like, before it tables its proposal in October? And then what conclusions do you draw from the unknowables that we're going to have? And I'd like to just discuss them at the moment, because this is kind of important at the end of the day. Because we're on quite a fast train in terms of designing the regulatory framework and the support schemes at member state level in the light of the European Recovery Plan for the future hydrogen market. And we've got a very short time to get this right. Because in October, the Commission will, as I said, table its proposal, which means basically it's got to be finished by June. Because June, July, August, you're on holiday. September, inter-service consultation, cabinet, et cetera, which means basically DG Energy has to get this done by the end of June, conceptually. So we don't have much time. And this is also very important because experience has shown that once you set the basic regulatory framework, which will happen by 2024, because it's going to take 3 years to negotiate the Commission's proposal, that sticks. It's difficult to change it once you're on that road. So it's very, very important to get it right from the beginning. And the questions that I've asked, what do we know, what don't we know, what additional knowledge needs to be done, and what conclusions we draw, that's normally what you put in an impact assessment. And so in a way, it's slightly worrying that the Commission's already reached conclusions on some of these issues in the hydrogen strategy before the detailed impact assessment, but that's another issue. So just let me make some observations on the what do we know, what don't we know, and what additional knowledge we should do and what conclusions we should draw. So what do we know for certain? The answer is not so much at the end of the day. We know that we're going to need an awful lot of low carbon or zero carbon hydrogen, or a combination of both between now and 2050. And we know we're going to need an awful lot of zero carbon hydrogen post 2050. Okay, so that we do know. That we do know. We know we're going to need an awful lot of hydrogen to replace the 8 million tons of feedstock hydrogen, which is used in ammonia production, methanol production, steel production today. And 8 million tons is a lot. In energy terms, that's about 10% of the natural gas that we use today. And in the future, it's going to be needed as an energy vector in relation to the hard to electrify sectors, transport for some cases, high heat energy intensive industry, and areas where consumers don't choose a rational electricity choice, for example, that choose not to have a heat pump, for example. So then what don't we know? What are the uncertainties? Okay. So first of all is exactly how much hydrogen we will need in 2030, 2040, and 2050. 2030, okay, the 8 million tons replace the feedstock hydrogen. That's pretty close. But once you get into in what it's going to be in 2050, they're a better person than I, because obviously for transport, there's the battle between electric transport and hydrogen transport. And we all say that, yeah, it's going to be needed for heavy goods vehicles. We'll see where electrification goes, but I think none of us know the answer today. It may be more or less. We just don't know the answer to that. In terms of replacing natural gas or coal in high heat energy intensive industry, I listened to a really good presentation from the Fraunhofer Institute a little while ago about an emerging technology of using thermal lances based on renewable electricity to heat it. So there's a lot of uncertainty there. But on the other hand, experience shows that people are slow to adapt to things. So we may get a lot of hydrogen in domestic heating because of inertia that people don't actually want or enable to put in heat pumps. We just don't know. There's an awful lot of uncertainty there. Secondly, we don't really know the relative attractiveness of blue, green, and turquoise hydrogen, both in terms of cost, CO2 profile, and environmental impact. And if I could just share my screen for just a little while. Jared, just check that that's coming up well.
Yes.
Okay, fine. This comes from a study that the Institute, the Florence School of Regulation did, Andres and I, with some researchers and Jean-Michel. And this gives the understanding of average levels of where we expect, sorry, not where we, where a consensus view of studies from the IEA, IRENA Commission and other sources envisage that hydrogen prices will be in 2030 and 2050. The point to make here is the margins between the high and low estimates are enormous. There's a huge amount of uncertainty here. But in terms of, if one unpicks it in terms of green hydrogen, there's a vast range, if you dig behind this, of the potential cost of green hydrogen in the future. On the very low level, there's the idea that one can produce hydrogen from renewable electricity from PV in very sunny areas, which would bring down the cost of green very, very high, very, very quickly. But on the other hand, why are you going to sell your cheap green, PV electricity to produce hydrogen if you can sell it into the electricity pool at a higher price? Secondly, there's the issue of water use in those areas. So there's some variabilities there. There's also the variability whether there will actually be physically enough renewable electricity to do the electrification and the hydrogen in due time. On blue hydrogen, There's the issue of cost, but there's also the issue that you've got to, if you build a blue hydrogen plant today, you've got to amortize it by 2050, because then it's out of the market, because it's never going to be a zero carbon hydrogen source. And so there's also the question whether technology will increase quickly enough in order to build it by a quick enough period by which it will be amortized by 2050. So there's a lot of uncertainty there. On turquoise, there's a lot of uncertainty, although the chemistry looks really, really interesting. Because to produce a kilo of hydrogen using renewable electricity from domestic turquoise hydrogen, it uses only 25% of the electricity compared to electrolysis, so renewable electricity. So there's an awful lot of uncertainty there, even though it's promising. Then in terms of the size and speed of the hydrogen grid that you need, obviously you need a hydrogen grid fairly quickly to prevent dominance and develop the market. And it's logical that you have to be ambitious here. But on the other hand, there's two big questions. You need to get it developed at the right speed, at the right time, to match demand as well as possible, not to overbuild it. And then there's also the question of financing it, because you have to build it too big in the beginning. So in the beginning, of course, the actual costs, sorry, the transmission fees will never cover the actual costs of the grid. So there's an important issue there. Then the next issue is the ETS switching costs and the logical speed of the transition. Now, I'd like to then show the next, if I can manage it. Yeah. So the other part of the study that we did was to try and examine, on the basis of these estimated hydrogen costs, or these consensus hydrogen costs, where the ETS prices might be needed in order to get low carbon or zero carbon hydrogen to replace existing hydrogen. So this is the feedstock hydrogen. And you see the huge variations that you have here in terms of the potential ETS prices needed in order to substitute this carbon. And what you do know, however, is that, so this is average renewable electricity, okay, using PV. This is the lowest cost. This is offshore wind, average lowest, okay. This is blue hydrogen, average lowest, and this is turquoise, average and lowest. So you see that some technologies for the 8 million tons of feedstock hydrogen that we're talking about, they're looking pretty good. So you can already start saying, okay, by 2030, yeah, that would kind of make sense. When you start, however, going to the high heat energy intensive industry, you start seeing very serious ETS prices that will be needed in order to get hydrogen used as an energy price. So there's also a great deal of uncertainty there. There's also a great deal of uncertainty of how you make sure that green electricity really is green. Because if you put an electrolyzer in some parts of Germany, for example, and you buy electricity in order to power it off the grid and buy some green certificates, and the marginal producer in the area is coal, the only thing you're really doing is increasing the amount of coal generation on the grid. So is it really green in those circumstances? So what conclusions do I draw from this? And these are some of the issues that I'm sure our panelists will be looking at, because the point I'm kind of making at the end of the day is we have to accept that to an appreciable extent, when the Commission does its legislative proposal, and as the member states design their hydrogen strategy, we're making policy in the dark to a significant extent, because there are so many unknowables. And this is not a criticism. This is unavoidable. Because if any of us is going to say what the technology in relation to electric vehicles or pyrolysis, etc., is going to be in 2030, let alone 2050, well, good luck on that. There's enormous number, and not just technological variables, there's an enormous number of market variables, because the relative competitiveness of these different forms of hydrogen, and indeed hydrogen as an energy vector compared to renewable electricity, will depend on the ETS price, the renewable electricity price and its availability, the gas price, the hydrogen price, and also the extent to which the IPCC and the Paris Agreement is working internationally. So this needs to be factored into the Commission's decision-making process. But on the other hand, we need to make sure that the market is market ready by 2030, 2040, and 2050 at the right place. So just four little observations from my perspective in this respect. The first is that the guarantees of origin, the first one is, to the greatest extent, the successful internal energy market principles, which are based on allowing energy sources and vectors to compete with one another, should underpin the development of the future hydrogen market, because that is, at the end of the day, what energy sector integration is. It's a regulatory system which facilitates all energy sources and vector to compete with each other on a level playing field for all energy demand, taking account of their relevant externalities, notably their greenhouse gas content. And so the way in which you design guarantees of origin to reflect that is important. The way in which you develop a no regrets gas grid quickly enough in order to prevent anti-competitive market dominance issues is important. And the way in which you use the internal energy market rules that have been enshrined by the gas directive in order to reflect this are really important. So Andries, I would like to finish my comments, my introductory comments there, and we'll pass it over to you for to introduce the panelists and start the debate. Thank you.
Thank you, Christopher. It was a great introduction, and it's also reflected on many aspects that basically we need to look in today's discussion. And I'm very happy that Barbara Jinks from IRENA, and she's dealing with green gas delivery and use, join us. IRENA has for quite a substantial time worked on the issue and developed a lot of proficiency. And it's also important to understand that green and low carbon hydrogen is not only EU issue. When I mentioned IEA Fatih Birol saying 40 million tons by 2030, well, EU ambition is 10 million tons, 30 million tons should happen somewhere else. So Barbara, now I give the floor to you, and thank you for joining the panel today.
Thank you, Andries and Christopher, and thank you for inviting IRENA to speak at this interesting panel discussion. Just to comment, Andries, on your last point, there are some major consortia around the world looking at up to 25 gigawatts of green hydrogen, and it's in feasibility stage at the moment, but there are very large global movement for green hydrogen. But I prepared a response to the question of the panel, which is, are renewable and low carbon hydrogen technologies ready for accelerated development? And I would like to share with you and the audience the outcomes of some research that IRENA has done recently, in particular on 2 reports that are available on the website. The key challenges, in addition to needing tailored regulation, as Chris mentioned, and a currently undeveloped market for hydrogen, cost is a major barrier to the uptake, the scale up and the development of green hydrogen. And I would like to outline a report that we have, research we've made into how to reduce the cost of green hydrogen. And the largest component of cost is the electricity, the renewable electricity for the production of green hydrogen. And the second largest component is the electrolysis unit itself. And it's important that green hydrogen, as Chris said, reaches parity with alternative fuels for it to be attractive and for it to be taken up. And the $2 per kilogram seems to be a benchmark from what we know now for competitiveness of green hydrogen. And electrolyzer costs have reduced over 60% in the last 10 years, but it's not enough. They need to reduce more. And the electrolysis technology is known. It's not an unknown technology. What is unknown, to follow what Chris was saying, is all the peripherals, the uptake, the policy, the regulation, the logistics. And the It's known technology, but it needs to be scaled up at a tremendous rate. And that also is an unknown. What's the speed of scale up and how is that facilitated? And we really need a step change in performance and the scale up to gigawatts, not megawatts, of green hydrogen to meet demand. So we've looked at this in detail, and the key conclusions that I'll share today is that in the best locations, leveraging on the best resources, hydrogen can already be made at a competitive price today, but those are in the best locations, the best scenarios. Costs can be reduced by 40% in the short term and 80% in the long term. And I'll share with you 4 key strategies for that. And there are clear opportunities for policymakers to influence the uptake and the development of green hydrogen. Sorry, Chiara, my slides. That was my introduction slide, so we haven't missed any charts. Thank you. So that was just looking at that. So can you go to the next slide, please? So the information that I'll share are available in 2 reports. The first one is a guide to policy making for green hydrogen, and the second one is hydrogen cost reduction by scaling up. And I've mentioned that the cost reductions can be up to 80% in the long term. And how do we achieve that? Well, there's 4 main ways. The first one is technical innovation. And that it sounds obvious, but we still have improvements to make with electrolysis design. The most savings we can make is reducing the stack cost, which is one of the main components of the electrolyzer plant, but also economy of scale, not only with the specialized units, but also the balance of plant, the power, the facilities, and everything else to do with the electrolysis plant. In particular, the materials needed for the electrolysis at the moment, the rare metals, are concentrated in 11 countries. And for example, the current production of iridium and platinum for some electrolyzers will only support up to 7.5 gigawatts, but we need over 100 by 2030. So a lot of improvements could be made in the procurement of materials and the logistics and the supply chain. And some electrolyzers, for example, don't need some of these scarce materials. So there's optimization that can be made in the materials. Number 2 is scaling up and the balance of plant, as I mentioned. If we increase the module size, it has a significant impact on cost reduction. For example, at lower manufacturing rates, manufacturing the stack part of the electrolysis accounts for 45% of the total cost. And at higher manufacturing rates, 15% is saved, which is a significant cost. And sometimes scaling up the overall plant can be a larger cost reduction than just scaling up the electrolysis production unit because of all the external facilities that are needed. Number 3 is the actual module design. Not all electrolyzers are the same. You can increase the module size, for example, from 1 megawatt to 20, reduces the cost by 30%. So there's a lot of consideration has to go into magnitude of production and demand and the whole system of supplying the green hydrogen for what end users. And that is affected by the situation. Is it a small off-grid production, or is it a large on-grid production, or is it decentralized? And they have different levels of flexibility and demands. And of course, everything is a trade-off between the lifetime, the efficiency, the cost, the throughput, the location. And the 4th cost reduction really comes by the natural learning, by doing the natural reduction in costs as we get to know the technology better, and as the systems are put in place and the whole supply chain is developed. For PV, the learning rates were up to 21%. That means 21% of cost was reduced just through us getting better with the technology. And our research, Irina's research, has shown that up to 40% cost can be reduced by through learning and the industry developing the green hydrogen. So the next slide, please, Chiara. So how does it look overall? This chart shows us that Today, the cost of green hydrogen can be up to $5 per kilogram hydrogen, and you can see that the first bar is the reduced cost in the actual electrolyzer unit, and that it can have the major impact. And then the next bar is the electricity cost, which is as important, if not sometimes more important than the cost of the units. And then those are the major costs that can bring the cost of green hydrogen down to below $2 per kilogram. And then, of course, in the future, there's other cost reduction through efficiencies, longer lifetimes, and of course, the cost of borrowing, the cost of capital, that has an impact. So the short-term cost reductions are more or less known, and that is reduced electricity costs, which is coming down all the time with the increase in renewable energy, and the 4 strategies that I've outlined with reducing the cost of the units itself. But of course, as Chris was saying, it's not known how fast these improvements will develop, and we can think about that, but we don't know until we start it. Next slide, please. What does that mean for the final cost of green hydrogen? This chart shows the results of our research with some variables in the electrolyzer cost, in the cost of renewable electricity, and assumed efficiencies and lifetime of the plants. And you can see that the green line at the bottom, by 2030, in the optimum situations, green hydrogen can be reduced to the benchmark of $2 per kilo. And it's a more widespread reduction in the future. And of course, that depends on all the unknown variables that Chris was mentioning. But in the short term, we feel that with concerted effort and incentive and a willingness that the cost can come down. Next slide, please. So in terms of policy, there are clear opportunities, and I think FSR, the team and the audience know very well what the opportunities are, that the key pillars for policymakers to drive down green hydrogen cost is to develop national hydrogen strategies. And by the end of 2019, there were 5 countries that had hydrogen strategies. And by the end of last year, there are 20. So we can see that that is taking place, and it's a positive sign. But then policymakers need to understand what the key targets for green hydrogen are and set priorities or targets. And IRENA supports the use of green hydrogen for the hard-to-abate sectors of aviation, heavy transport, heavy industry. And the policymakers can also provide certification and the guarantees of origin to allow consumers to be confident of what they're buying and what the carbon content of the fuels are, and to allow market to be able to develop with certainty. And of course, as Chris was saying, adopting enabling policy, we need that as soon as possible to enable the market to develop. Different policies have different effects at different times, and the chart, you can see this is a summary of what we felt was the timing across the stages of developing green hydrogen, starting with long-term signals from market. And I won't go through them because these slides will be shared, but investment, R&D, international cooperation are essential to develop green hydrogen as a new commodity to the scales that we want, and facilitating investment, establishing regulations and designing a market that supports the scale up of green hydrogen as a priority, and looking at, as I say, adopting policy to facilitate more optimized procurement and logistics and the material sources for the electrolyzers, and to foster coordination. That's absolutely essential. And the public-private partnerships has been, is also a promising development that needs to be developed a bit more. The overall message is that there are opportunities and it is feasible to reduce the cost of green hydrogen, but with very focused effort and a desire by policymakers and the market for this to happen. Thank you.
Thank you very much. It was very clear and very comprehensive presentation. If I may just to ask a question about your stakeholders. ARENA is very broad stakeholders, and most of them definitely are very much interested in power prices, so electricity prices, less perhaps on hydrogen. How broad the front now is that are keeping the interest in renewable hydrogen? Is it only Europe or it's a bit broader? Are there some other regions that have interest in it?
Oh, absolutely. It's not just Europe. So ARENA has 163 members, and there is a lot of engagement by the members into green hydrogen actively, but also countries just looking and at a very early stage in thinking about it. But last year, the members requested and mandated ARENA to focus on green hydrogen as an opportunity for low carbon fuel. And to that end, ARENA has set up a collaborative framework for green hydrogen. And that is the main aim is to allow the interested countries to get together in a focused arena, but also to allow private industry to be involved in that. So it's a bit of a new model for ARENA, and we're kicking that. We've had one meeting, and we're in at the end of the second, around about March, we have another meeting, and we have a lot of interest, in particular from Australia, Chile, Europe, Middle East, I have to say. Exporters and importers. It's a clear supply and demand interest. And there are some major consortia, as I mentioned before, looking at, for example, 25 gigawatts. And that is through a global chain of producing in countries that have a lot of excess renewable energy to the countries or to the regions like Europe that want the green hydrogen. Australia, for example, has 3 MOUs with Japan to supply green hydrogen, 2 through green ammonia, and 1 announced just last week, which is actually in the form of liquid hydrogen, so a different model. So there's a lot happening, Andres. They are at early stages, but money is being put on the table to do feasibility studies, and there's a lot of commitment there. So we see promising developments.
Barbara, can I ask a question as well? Because I thought your slides were really convincing about the opportunities of getting green hydrogen to very, very competitive levels. As you say, because it's an OPEX-driven product at the end of the day, the cost of renewable electricity is fundamental to this. And your numbers are $20 a megawatt hour. So it's about 15, I suppose, 15 euros a megawatt hour, something like that. So my question is the following. I mean, what we've seen in terms of ARENA IEA price forecasts, large-scale offshore wind is not going to get down to that level anytime soon. But what is likely to get down to that level is PV in sunny places, basically Australia, Chile, parts of Southern Europe, Northern Africa. And so there's 2 questions I have in that respect, in terms of whether we'll be able to get down to those prices and how quickly. Because, you know, the first one is if I put up a big PV panel somewhere, anywhere, and the pool price is a balance between the PV and the offshore wind, then I'm going to want to try and sell it for the higher price in the pool rather than use it for hydrogen. And secondly, there is the issue of water availability in these sunny areas. So do you have does ARENA have modeling or predictions as to how quickly we'll actually be able to, as in a real market model, be able to hit those prices to enable to get us that €2 or $2 hydrogen? Because it just instinctively, it seems a little bit unlikely by 2030. So it's, to what extent or how do we get there?
So to be honest, Chris, I personally can't answer the question right now because I wasn't involved in the modelling and I'm quite new to ARENA. So, but what I can say is the chart on my slide showed that even with an electricity price of 65, you can still reach the $2 per kilogram by 2030. And that's the slide with the range of costs coming down. So it's not at that optimum of 20. Something else I've noticed recently, there's an MOU between an Australian company and Indonesia to produce green hydrogen, and they're looking at hydro. So it's not just windmills and solar panels, and there's some massive excess renewable energy around the world from hydro as well. So it's a bit more of a mixed bag. And I hope that answers your question in some form, but I'm very happy, Chris, to actually put you in touch with the people in ARENA who could answer that question better than me, if needs be.
It answers it really well, actually. Thank you, Barbara.
Oh, okay. Thanks.
Thank you, Barbara. Our next panel member that I'm now introducing to you is Kees van der Looyen. Kees works with these issues for substantial time. He's director and Guidehouse. Kees, please, the floor is yours.
Yeah, thank you very much. I would like to start on the North Sea, and that's close to home. I'm based in the Netherlands, and where we're doing work for the North Sea Wind Power Hub Consortium, and that shows you a little bit about the topic of system integration that I would like to touch upon here. That's a consortium that's of TSOs, electricity and gas TSOs, that's getting their heads around how to integrate 180 gigawatts of offshore wind from the North Sea into the Northwest European energy system. And for them, we've done a lot of work. We're still working for the consortium, but one of the studies, which is publicly available, by the way, is integration routes, where we've done detailed modeling to see how this capacity of offshore wind could be effectively integrated in the energy system. And the question came a little bit from electricity TSOs, scratching their head to see can we really build that much of electricity transmission, because this is by far world's largest power plant. The system was built for 1 gigawatt size or a few gigawatts, and not for 180 gigawatts. So it's 6 times as big as the Three Gorges Dam in China, for example. But what we found out in the modeling is that at some point, it doesn't even help to build more electricity transmission infrastructure, because on a moderately windy day, all of the demand, including additional demand from electrification, etc., is already covered in Northwest Europe. And you actually have a problem in time more than a problem in place from that point onwards, because on a very windy day, it would not make sense to build more electricity transmission because the demand is not there. Of course, you can improve it a little bit by demand response and building even further interconnectors, etc. But there is a point at which your main issue is a problem in time. There are days and weeks with a lot of wind and solar, and there are days and weeks with less, and you would like to store it. So what we have looked into for the consortium is how a combination of electricity and hydrogen infrastructure could help integrate this amount of wind energy, and then that even if you only take the electricity system itself, you need also dispatchable power on those less windy and sunny days and weeks, and you could do that with hydrogen. It can be used in gas-fired units, which have a relatively low capex investment cost per kilowatt, which makes them suitable to run at a low capacity factor, and also a high flexibility. So there you see how the whole thing is intertwined, and it's not like, oh, this is the gas sector against the electricity sector. We're looking for integrated solutions to get to net zero emissions in a reliable and affordable way. And that's what we also do with a number of gas TSOs. And I would now like to share my screen. Give me a second and tell me when you see it. I'm sharing at this point in time.
We see it. Yes.
So what I would like to tell you a little bit about is a project that has emerged from work for Gas for Climate, a consortium of biomethane producers and gas TSOs, where the gas TSOs figured that they were all working in some shape or form on the role that their pipelines, their infrastructure can play in bringing hydrogen in future from supply to demand, and where we brought them together in a group joined by Net4Gas from the Czech Republic, adding up to 11 gas TSOs at the time, in a period from May to July last year, to see whether they could come up with a coherent plan for a European hydrogen infrastructure. Because as you've already heard from the introduction and from previous speakers, this will be a very large-scale vector, and you will have suitable sites for producing hydrogen, and you will have different sites, for example, industrial clusters where a lot of it is used. So there would be a case for a European infrastructure of hydrogen, and the gas TSOs have got together with us to see how this could be done and on what time frame. And I will not show you many slides, just 3 for now. But this is what, for example, could be done in 2040. Starting from some emerging regional networks in 2030 and connecting more and more by the middle of the 2030s, you could get to a hydrogen backbone, a true hydrogen backbone by 2040. The green countries are the countries that were a member of the group at the time. The group is actually expanding now. National Grid from the UK has joined, and Gas System from Poland, DESFA from Greece, and TAG from Austria. So we're now in the second phase of the work, but at the time the green countries were participating. And you can see that such a network could already stretch over 23,000 kilometers, consisting for 75% of existing natural gas pipelines, which are technically suitable to carry 100% hydrogen, and 25% of some necessary stretches of new hydrogen pipelines to come up with this consistent network, acknowledging that by 2040, it's probably also necessary to still supply natural gas. So you cannot at will, at random, change natural gas pipelines to use them for hydrogen. The capacities are quite substantial. Those pipelines have a diameter ranging from 24-inch, so 60 centimeters, to 48-inch, 1 meter 20. And those pipelines can transport 3 gigawatts of hydrogen for the smaller one, and up to 13 gigawatts for the larger one. That's a little bit less than you see in some other studies, because what we found when we looked at the cost is that it's probably better not to try to transport the maximum amount of hydrogen through the pipelines, because that costs you a whole lot of compression cost. So if I go to my second slide, that's a little bit about optimization. If you look at how to dimension such a network, you look at the pipeline parameters, the given ones of the existing pipelines, and the ones of new pipelines where you have more freedom of choice. You look at compressors, that's really big difference. So on speaking about technology, the compressors needed for hydrogen transport are bigger and more complicated than for natural gas transport. A lot of work to be done there. You look at pressure requirements, also at the delivery point, what pressure is needed at the end of the pipeline, what can be supplied at the beginning. And you look at all kinds of CAPEX and OPEX trade-offs. And there we found that in the end, it's probably, as I already said, better not to maximize the hydrogen flow, because that would lead to disproportionately high compressor capacities needed and electricity to run the pipelines. What we find is that if you go a little bit lower and take like the 13 gigawatt capacity for a 48-inch pipeline, then you only need like 2% of the energy content of the hydrogen flowing through the pipeline to transport it over 1,000 kilometers. We have also tried to come up with cost estimates for such an infrastructure. Of course, it's a wide range because there's quite some uncertainties, especially on the compressor side, even considering locations and the electrical connections needed at the location. But roughly the investment cost of such an infrastructure that I showed for 2040 would be 30 to 60 billion. And if you take into account the cost of compression as well, the OPEX, the operational cost, then that translates to transportation cost of around 9 to 17 euro cents for a kilo of hydrogen, of which Barbara showed the production costs over 1,000 kilometers. So if you're talking about $2 per kilo hydrogen, let's say €1.60, €1.70, then for less than 10% of the production cost, you can transport it over 1,000 kilometers. So you have a much bigger addressable market for supply projects and a much bigger area from which to source your hydrogen if you're, for example, a steel company needing it for your decarbonization. So that's for now what I would like to add to the discussion. This is kind of an offer by the gas infrastructure companies to the European hydrogen economy. And of course, yes, they want to reuse their infrastructure, but that's no different than electricity transmission companies now offering to carry renewable electricity from A to B, where in the past they used it to transport fossil electricity from C to D, right? So it's a piece of the puzzle, and what we're doing at present in phase 2 work is talk to many stakeholders on the supply and demand side, but also on the market operators, equipment suppliers, etc., DSOs, distribution companies, to see what such a backbone could mean to them. And so far, we're getting a very positive response about the boost that the availability of such a transport network could give to the plans on both supply and demand side. I would like to leave it at that for this moment for my contribution. Thank you.
Thank you, Kees. As usual, very well and clear delivered message. I have a question from audience. The audience asking is, it's Michael Jensterle. He asks, or he or she, it could be, did I understand correctly that existing pipelines are suitable for carrying 100% hydrogen? And there's like a sub-question, with adaptation or without? If I could add one also note for the hydrogen backbone. At some stage I heard from European schools that for most students at the school, Europe ends more or less with Berlin. Whatever happens else is, well, just one big spot. And I think with this map, you immediately broke. I understand the answer, but there should be something, because the perception is that it is only for a couple of countries involved and some countries are not involved. I know it's work in progress, but it would be nice that you somehow find a way to adapt it, because I know that Portugal is also like isolated, but this is something that could lead to some misunderstandings later on. But the question from Micha, please, Kees, that's a question that I would like to ask you.
Thank you for two very important questions. First, on the suitability, it's not a law of nature that natural gas pipelines are suitable. It depends on the steel that has been used to produce them. But with all the participating TSOs, we found that their transport pipelines are suitable for 100% hydrogen transport. And that's what we're talking about here. We're not talking about blends in this backbone project, although that's also a possibility. We found that they are suitable without major modifications, so you need to do some cleaning, etc. You could apply a coating on the inside, and that's an optimization question. It's not a necessity, not a technical necessity. The coating could, for example, allow for higher pressures and higher flows of the hydrogen. So that was quite intriguing, and that means that the cost of these pipeline sections where you can use converted pipelines are only like something like 10-20% of having to build a new one, which is then obviously pretty similar because they are already suited for hydrogen. Then the compressor cost becomes the dominant factor. And the good news there is that you can have kind of a growth scenario. If you would build a pipeline and it would not be fully utilized in the beginning, it would be served to also stimulate developments on supply and demand side, then you don't need big compressors, because the lower the flow, the smaller the compression needs, the smaller the pressure differences over the pipeline. So you can start relatively simple, and as demand grows, you can grow the compression capacity as well. So no, the pipelines are suitable, and the big difference is in compression, I would say, on that question. And then to your question, Andres, yes, it was a very pragmatic start with the gas TSO members of the Gas for Climate Consortium, already at short notice joined by Net4Gas from the Czech Republic. But we're very happy now to speak with all European gas TSOs and many other stakeholders. And we find a lot of interest from all over Europe. This has already led to Gas System of Poland and TAG of Austria, DESFA of Greece, and National Grid joining. But I think you'll see a few others joining, and this is becoming more and more a pan-European effort. And that's also what it's actually the last box on the slide that I'm showing right now. It's an open initiative. That's already what the gas TSOs that kicked it off were hoping for. They would like to cover the entire EU, and they extended an open invitation for others to join.
If I may, immediately, Christopher, sorry, I saw the questions that very much related to the issues that was now answering Keith. Anne Hutman is asking, is Nord Stream 2 ready for hydrogen? And Russia having a strategy to export clean hydrogen to EU. Well, I think a lot of people would be interested, yeah.
We haven't looked into Nord Stream 2 yet, but yes, it's of course interesting to see what Russia could mean in the hydrogen economy. It could be something with turquoise hydrogen. It could be blue, but then it could also be that natural gas is still imported and turned into blue hydrogen in the European Union. So there's many open questions, and we hope also to speak to players from that side pretty soon. One point about Christopher's introduction here, we see the opportunity to also fully decarbonize blue hydrogen. In Gas for Climate, we already said that for new installations, you can reach something like 95% carbon capture. If you use autothermal reforming, that's going to be easier. The way to get to 100% there would be to feed in 5% biomethane into the mix to make sure that you have effectively some BECCS bioenergy with carbon capture and storage to compensate for the 5% remaining fossil emissions. And actually it opens the way, if we will ever need it, to negative emissions, because you could use this blue hydrogen infrastructure to operate it in a BECCS mode, in a bioenergy with CCS mode, by feeding biomethane into the reformers and into the carbon capture and storage system. I'm not saying that this is a given that this trajectory will be followed, but we need some options, right, also for negative emissions, and this could be a very pragmatic way of implementing BECCS in such scenarios.
Yeah, Kees, I also had a question, which is obviously the exercise of designing this this backbone has not just been taking a felt pen and drawing lines on the map. Obviously, there's an attempt to make sure that it's scaled enough to meet demand, but small enough not to create stranded assets. So my question is, how have you done that in order to try and reflect, well, to make sure that European consumers are not going to end up paying for steel in the ground that's going to be used to a small amount, and that it's going to be big enough to make sure that it facilitates the market? How do you see the planning process developing to make sure that that is reflected? That's the first question. Secondly is, how do you finance the thing? Because you've got to build it future-proof. So, you know, when you build it, it's like building a new motorway. When you first build a new motorway, there's relatively few cars on it. So the cost per car is very high. So have you thoughts on how to finance it? And lastly, could you just comment a little more, because that was news to me, on the blue hydrogen thing that you mentioned. I'd always understood that blue hydrogen could only sort of SMR and CCS could only get 90% of the CO2 out of it. So is that a new technological development?
Okay, maybe to take that one first, because it connects immediately to my previous point. If you add carbon capture and storage to existing gray hydrogen production with steam methane reforming, the easy part is to take the CO2 from the process gases. That's 65% or so. So and the hard part is to also capture CO2 from the combustion process in there, which could get you theoretically up to 90-95%. If you would build a new blue hydrogen facility, you might also opt for autothermal reforming, a different process of producing hydrogen from natural gas. And that makes it a little bit easier to reach 90-95%. That's I would say, the technical upper limit. What I was describing is that if you don't feed 100% natural gas into that system, but a mix of 90-95% natural gas and 5-10% of biomethane, then you're effectively canceling out those CO2 emissions by the biomethane component. And then you get to a net zero carbon emission type of hydrogen. If you increase the amount of hydrogen, of biomethane, of which you capture, it's a way to get biogenic hydrogen taken from the atmosphere by the plants into the ground, right? So if you increase the share of biomethane beyond 5 or 10%, you get into net negative emissions territory. So it's like a continuum, first pushing the limit technically to that 90 or preferably 95%, and then seeing if you would like to get rid of the 5% or even turn it into net negative by putting biomethane in the mix. And then, of course, you have to look at the alternative uses that you could also use the biomethane for. So it's not a free ride there. Is that clear on that one?
Yeah. Then
not too big, not too small.
If you have any scientific studies to share on the costs, etc. So if you have any links to share on the scientific basis, that'd be really interesting.
Yeah, all the reports that we did for Gas for Climate and European Hydrogen Backbone are are as transparent as possible and publicly available, but I will share links with you after this. So it's on the Gas for Climate website. Not too big, not too small, very important, yes. I think this is just a first go. We came up with kind of a minimum viable large-scale transport network as an element for the ongoing debate in the EU about how big this thing will be and where will we get our hydrogen from. That's actually a part of the phase 2 work that we're now looking at the supply side. Okay, if you want 1,000 or maybe 2,000 terawatt hours of renewable or low carbon hydrogen in your system, where do you get it from? How much gigawatts would it mean, and could you do that domestically within the EU or import it? So it's you have to get to those low prices of transport. You have to do it at some scale, at the scale of one decent pipeline per country connection, I would say. So this is like kind of a minimum viable product for a European hydrogen backbone, but it could be expanded, it could be bigger, maybe it could be quicker. For example, the steel industry is now asking us, it's a very nice initiative, we would love to be connected, but can't you deliver before 2040? Because we need more renewable and low carbon hydrogen and we need it earlier. So it's just a first element for the discussion. It's not a given, this specific dimensioning. So you can figure that most of those connections are around 7 to maybe 13 gigawatts worth, and that's already a lot if you compare with the few gigawatts of electricity connection that we managed to build from Spain to France over the course of time. Financing, yes, very important. You would like, there's a lot of low interest money looking for this kind of infrastructure projects. Of course, we see a lot of interest from institutional investors, from pension funds and the like, but then it's all about risk. So what will there be a kind of an income certainty for the operators of these pipelines, and that is, I think, a societal choice. So if you wait until there's full certainty of a high utilization of a pipeline and then get it going, then it's not going to be the enabler of hydrogen developments of the supply and demand, on the supply and demand side that you would like to see. If you would like to go first with your pipeline, then you need some regulatory means to recover a modest return of investment. So charging the cost on the gas network users or some kind of investment support or whatever. So financing is not going to be a big issue, but it is there needs to be a societal choice about are we willing to pay for this, even if in early years it isn't fully utilized. And if you would like to charge the first use on the first two customers on the supply and demand side, then it will probably become prohibitive. Then they will say, okay, no, thank you, we won't do the project. So that's the puzzle that we hope to be part of solving, but that requires a lot of thinking and a lot of initiative also on the Commission and the national government side.
Yeah, thank you, Keith. I see that Yorgo Chatzimarkakis, Secretary General of Hydrogen Europe, has joined us. Yorgo, I think you have in this job since 2016. Is this the year where you expect that all the things that you expected from when you joined will be materializing, or there are serious barriers with development of technologies or some other issues related to deployment of green and low carbon hydrogen? Please, Yorgo.
Many thanks, Andris, a lot of things that we both put on rail when we were in different schemes. You were commissioner, I was in the Energy Committee of the Parliament, like ACER or REMIT, so things that are very important today, play a role in the implementation. but I don't go into detail. I just wanted to give one snapshot on one question that has been raised. That's Nord Stream. I don't want to forget this. Nord Stream people, or especially Gazprom people, tell us that this pipeline is 80% ready, which means the pipeline is ready, the compressors are not. So it is the 20% missing are the compressors, and I think Case made this point very clear that most of the pipelines are suitable. Now, is this the year? I think yesterday Mrs. von der Leyen, Ursula von der Leyen, gave a speech that was quite, even for me, it was surprisingly courageous when it comes to the timeline. So she gave a 10-minute speech to the Hydrogen Council, which is a global club of CEOs with, I think, more than 50 members. And she said clearly that this is a central part of the energy transition. And yes, indeed, I started 5 years ago, exactly this week, 5 years ago. And I have to say that the pandemic, of course, helped like a catalyst to make things much faster. One central element of the implementation, I will explain how we are planning that, is this RRF, so the Resilience and Recovery Fund. And we see more and more member states announcing the figures that that they are putting into that instrument. Not granular so far, but just the dimensions. Now, what is the plan? You see behind me, and that's one of the reasons why I was a little bit later in joining your important conference, and I left this. It was the first official meeting of the European Clean Hydrogen Alliance Sherpas, so the guys who are preparing that. What are we doing there, and what are we planning there? We believe that this year, 21, is the year of engineering of projects and of finances and funding. And basically, the European Clean Hydrogen Alliance is one of the major tools to bring that together. So we will deliver until May a so-called project pipeline, whereby all 6 parts of the value chain, from production over dissemination, and then the use and mobility in residential heating, in industry, or in energy balancing, are integrated. And the project pipeline basically is something like a seal of quality. This is a project that you, Germany, Sweden, Latvia, you can go back to if you want to use your resilience and recovery fund means. So we want to give some quality proof to the projects. The project as such will be, as I said, engineered during that year and started to be implemented as of 22, including what Case just mentioned. So building up the backbone, because most of these projects go for the first wave, which is the low-hanging fruit, decarbonizing hydrogen as a feedstock in industry. So basically replacing gray hydrogen by green or decarbonized hydrogen. This needs, of course, this backbone, and that's part of the overall project design. Now, in parallel to that, and this is very important for me to say, we also work together with Executive Vice President Vestager, Margarete, on state aid rule flexibility. Because it goes without saying that all this is not possible. This is a systemic change, disruptive. It doesn't work without massive funding, not forever. We foresee for that funding period 3 years. So 22, when the reform of the state aid will start to be put into practice, until 25. 3 years where we wish to spend money, public money, but also to attract private investment in order to go for big demonstrators, for big pilots. We need, and we have a clear target, the target that is given to the European hydrogen industry by the European Commission. And the strategy is 6 gigawatt of capacity until 25 and 1 million ton of renewably produced hydrogen. And that's a clear target. And we are now basically starting to put this into practice. We are very happy that the instruments that can be used, like the IPCI instrument, Important Project of Common European Interest. This is an instrument to make state aid help better applicable. And Mrs. Vestager said, this is what we're going to change. In the end, I believe that 70% of our project pipeline will come from that instrument. And indeed, we can see that member states have already earmarked money for hydrogen in the range of 45 billion euro. So 45 billion euro for the next 10 years, that's remarkable. At the same time, the first meeting with industry that happened right now, so with industrial partners, said, we don't just want the demonstrators, we also want to see the market, so to say, regulation. We want to see a regulatory framework, whether it makes sense to invest. And this is something we do in parallel. We don't believe that market incentivation or market elements will be in place before 25, but as of 25, we want to see them working. And then we have reached, and Christopher will like that idea because he is one of the conceptual masters of this. We will have reached a quite considerable volume of hydrogen production and the prices will go down, and we avoid the same mistakes that we did in similar fields. I can only give you the figures as a result of the damage that has been made to taxpayers and consumers in green electricity by prioritizing it, which was the right way to do. Don't get me wrong. I'm not arguing with prioritization, but I'm questioning whether the instrument that has been chosen, feed-in tariffs, was the right thing. So the Germans have just published their figures, and for the last year, the damage to the grid, or the recompensation, let me put it like that, the recompensation that had to be given to electricity producers was 30.05 billion in 1 year. The curtailment was 1.3 billion. So 32 billion for prioritizing something and not seeing whether we have the right capacity. We don't want to do that again. That's why we go step by step. That's why we think this timeline this year engineering, as of 22, 3 years pilots, and as of then, indeed, market is the right way to do. And we are very happy that the different instruments that are in place time-wise fit very well. The project pipeline will be presented in May of this year already. And until then, also the RRF plans of the member states will be checked and will be assessed by the European Commission. And then we can go granular. Notification of first projects is planned for November this year. And then, as I said, implementation. I think that explains a little bit that we are both in a rush, but at the same time, really happy to go for quality and not just quantity. Thank you.
Thank you, Jorgo.
Andries, I know we have to jump straight to Ronnie, but can I just make one very short comment to Jorgo? That I would argue the word damage from the feed-in tariffs and the subsidies is the wrong one. I would say it's cost, because when the renewables revolution started in 2009, you really needed feed-in tariffs to kickstart an industry from absolutely zero. And whilst with the benefit of hindsight, one might have done it slightly different in terms of timing, I wouldn't use the word damage. I'd use the cost, because on the other hand, it's given the European taxpayers a great deal of good things, which is a much cheaper renewable system, which wouldn't have happened without it. But you're absolutely right. And I fully applaud your comments that we have to learn from those experiences, because the hydrogen market is really different than the renewables one. And so I really strongly support your comments. Back to you, Andries, sorry.
Yes, thank you. Well, if I may, we will have possibly some discussion, but let's move to Ronnie. Ronnie Belmans is professor at Leuven University and chief executive officer of Energiewil. And Ronnie is, he's with hydrogen, I think, earlier, since his hydrogen policies have been developed. But I think what he looks at is It's a facts, facts, facts. And it's a lot of the inspiration also around hydrogen. So now we will try really to go to facts. And Ronnie, the floor is yours.
Thank you, Andris. I will share my screen to... Do you see it? You see me, you hear me?
Yeah, it would still need to be full screen, otherwise you get Chiara after you.
No, it's perfect. It's good. Okay. Go ahead, Ronnie.
Go. So, very interesting presentations, very intriguing, and I'm glad to be here. And when Andris phoned me, I said I have in January another seminar on hydrogen, sustainable molecules, etc. Would you like to join me? Because I want to organize that seminar in the idea that 1 year ago we were quote unquote sitting together here also, and what has been changing. And he also put it to Jorge, why do we think that it's going to be accelerating extremely over the next time when we will see it? Also what Christopher is saying on that. What has been changing? Why are we looking at things? What should we do? Where do we have to go to, and what should be happening? And to be clear, the first thing I did is have a look at what is changing in 2021, what did change in 2022, what's going to be changing in the next years to come, and then how are we going to go ahead? And for me, it is still unclear. And I want to give you some numbers for discussion, thinking, and way of thoughts. I think there is a long route to go. There is a lot to do. A massive amount of hydrogen and sustainable fuels will be needed. And I would like to point to where, from a technical point of view, the challenges are, and the challenges are not to be debatable. And then you have the challenges that could be there. And then there are things we better do electrically and with energy efficiency. So that is the idea. So I reverse the whole thing. I hear a lot of speeches and a lot of talk about how much hydrogen that we can make. But the question is, where are we going to use? Is there a pool? Is there a demand? Is there a need? Because, and that's the most important thing, I'm a dumb engineer. What are my laws that are governing it? These are the laws of thermodynamics. And the first law of thermodynamics is that there is no energy problem because energy is conservative. But the quality of energy goes down every time you change it from shape. Every time you go from one energy vector to another vector, you lose quality. And there is a term in engineering which is describing that, which is called exergy, and I'm not going to use it. But make it clear, if I have electricity, I can make almost 100% mechanical work out of it, having done something. If I have heat at 60 degrees C, I can't do anything working with it. So that's the quality. And as each time you change from one type of appearance to another type of appearance, things are going down in that quality. And that's why we as engineers have the fundamental law in our thinking that's hammered in from day one. Don't change the appearance of energy if you don't need to do it. So if you have an appearance, say electricity, and you need electricity at the end of the road, in between, don't do anything else if you don't have to do it. What also changed in 2020, and that's from my point of view, one of the, and I'm looking at it, when reading at it, I was amazed and surprised by the fact that the communication 299, powering a climate neutral economy and a EU strategy for system integration, is really writing down in legal terms the physical law which I just explained to you. So first, reduce the energy demand, so energy efficiency first, then electrify whatever can be done electrically. So if you have electricity from PV or for wind and you can use it electrically, don't do anything with it. And if 1 and 2 don't work, promote renewable and low carbon fuels, including hydrogen in hard to decarbonize sectors. And then they enumerate a number of those fuels. So I was really surprisingly and very happy to read that, because that fits with my way of thinking. And what are those hard to abate applications? They always are enumerated: industrial processes, transport modes such as aviation and maritime, and then there are also a number of potential criteria listed in that thing, being captive fleets of buses, heavy road transport, etc., and industrial applications, steel refining, etc. Now, in order to have a look on how much it is, we did a very rough and high-level study on energy demand as it is now. First of all, you have, of course, hydrogen, and hydrogen to stay now roughly 10 million tons, as we all know, in EU, and that has to be supplied. Be careful, this is not sure, because if we are going to go to a fully decarbonized system by 2050, and you see here on the slide that 25% of the hydrogen demand presently is going to refineries, what will be the refinery request by 2050? If we all are going to drive either electrically, which I think, or with carbon neutral fuels, is there going to be any refinery left? So we have to be careful that we don't think that things are going to be the same always in all energy supplies. But if we look at transport, you have here enumerated the whole different approaches, all different transport needs. And we start from the need of what type of transport there is. And if we can come to cars, land transport, e-bikes, and you see that all European manufacturers of cars are going electric, period. There are no hydrogen cars available except in Korea, South Korea, and Japan. Toyota is still working on it. Hyundai is still working on it. But in general, in all paperwork that you have, they are not counted anymore into the hard to abate applications. So let's forget about cars, certainly in the long run. There's many battery manufacturing investments in Europe going on, as well in the Nordics, and also the Tesla near to Berlin. And we see electric trucks are taking off, like with Volvo, like with Tesla and other ones. But just to give you an impression, the present energy use for this land transport is roughly 3.3 pentawatt hours, so 3,335 terawatt hours. And if you could electrify this, you end up with an electricity demand of 1,100 terawatt hours. So yes, we can imagine to electrify that 3,335 terawatt hours, but it would put a burden on the electricity system of 1,100 terawatt hours. To give you an idea, if you go to Eurostat, EU 27 requires 2,500 terawatt hours now. So this would have a serious burden on it. But of course, if you want to do it with sustainable fuels, you have to multiply this by the reverse of the efficiency of the whole system, which would lead at least to a doubling, roughly 2.5 higher demand on electricity than the 1,100 terawatt hours. What is certainly to be abated by fuels, as we know now, technology-wise? Shipping and aviation. There is no real technology pointing to the fact that we have long-distance shipping and aviation being electrified in the decades to come. Maybe wrong, maybe there is a big breakthrough, but I can't find it. And if you look at the Eurostat statistics, the fuels for shipping and aviation are difficult to find because they are not in the regular fuels. But if you look at it and puzzle a bit, you get to roughly 1,053 terawatt hours of liquid fuel being used for shipping and aviation in Europe, bunker fuels, etc. These have to be substituted by those synthetic fuels, by hydrogen-based fuels, which have to be produced. If you look at buildings, and I know what Christopher said about the, say, inertia being there, and I fully appreciate that. But if, as a technology-wise, is it possible? If you do the analysis, you get in the residential buildings a demand of 2,851 terawatt hours. A lot of it is biomass, is also the heat networks, is also electricity demand. And there is 1,245 terawatt hours going into residential buildings being natural gas and petroleum. If the renovation wave would be successful, there would be 75% less demand on that. Leads you to 300 terawatt hours of heat to be supplied to residential buildings. These are rough numbers. You have to be doing modeling much more carefully, but to give you an order of magnitude. If you do that, you need roughly 110 terawatt hours of electricity. For commercial buildings, you can do the same exercise and you come to 50 terawatt hours of electricity. So if you go full into the direction of heat pumps and supply of the remainder heat from the ground or from a carbon-free heat network, you come to an extra demand of electricity of 160 terawatt hours, roughly. This is feasible, but as Christopher said, it will take policy and a lot of pushing and a lot of good design of buildings, because the heat storage is important and the building design has to be really in accordance to that heat storage, which is not easy and will cost a lot of architecture thinking. In industry, the overall demand of energy is 2,860 terawatt hours. And together with Piero Dos Reis from FSR and other people, we have been looking at the Eurostat statistics, also GRC people. And if you look at those statistics, they are very difficult to interpret. Sometimes they include process energy and process fuels, so being part of it being for feedstock. But how, if you want to include, for instance, electricity going to hydrogen and used again for electricity, those things are not included. So these statistics in Eurostat have to be modernized to go for these renewable surroundings with feedbacks from electricity to sustainable fuels and back. So there has to be a very careful analysis on that. So the industry has two groups. Some of them are centrally located and some of them are more distributed. And for the centrally located, you can think of producing the hydrogen or the synthetic fuels on the spot, and also the production of those synthetic fuels can be either centrally or can be imported from other countries. Just for the sake of completeness, you get here the list of industries which are in Eurostat. And you see that if you look at iron and steel and chemical and petrochemical, we have an awful lot already covered. Very important is also non-mechanic minerals, reed, cement industry. And just to give you two examples, because we are working now, we are beginning our really going in scrutinizing the difficult industry sectors. But just to show you the difficulties, if you look at steel industry, there are three ways of making it carbon neutral. They are summarized the three first bullet points. And one of them that has been a lot in the media these days is the H2DR, the Swedish approach, which is now being constructing upwards to 2026, first pre-commercial small set to make it from paperwork to a first tryout in the R&D process. If we go into that direction, and if we go, then the numbers say you need 3,200 kilowatt hours per ton electricity more, which includes 2,600 kilowatt hours per ton for the production of the hydrogen. Now, if you do a ballpark calculation, and if we have 169 megaton of steel per year in Europe, it would lead to 540 terawatt hours of electricity in order to decarbonize roughly 200 terawatt hours of carbon-based fuels today. Just to give you an example, 2,500 terawatt hours of electricity used in Europe today would add up only for making steel carbon neutral 500 terawatt hours. And that includes a large chunk of hydrogen. This is the process, very interesting technically, but a lot of energy challenges. If you go for petrochemical, as I said already, the hydrogen demand will drop in refineries. And if you go to chemical industry, there are a lot of routes. And also if you're discussing hydrogen, or I would rather discuss it, the carbon neutral fuels, you have the bio-based chemistry, you have a lot of circularity in plastics that are possible, you have electricity-based hydrogen for ammonia production, and you have other electricity-based hydrogen production. You have CCUS being blue or turquoise. And just to give you an idea, at this moment, 262 terawatt hours is already used in chemical industry. Only for ammonia, it would require 161 terawatt hours of electric energy to decarbonize the whole ammonia cycle. So this would be a flow of it, but that's still under a lot of debate. What will be? Will we import the molecules, or will we produce them close to Europe, or will we produce them close to the demand? Still, a lot of things have to be done. And I was very intrigued by the numbers that Kees showed on the flows into in the hydrogen pipelines. We really have to look how much the different parallel flows can be in power. It's going to be a very interesting scientific debate on that. But as a conclusion, and the message I want to bring, there is a lot of work to be done to produce hydrogen and synthetic fuels, which are unavoidable for the time being, as we know. A lot of it will be in transport, aviation, certainly, shipping, certainly. Road transport, as I said, we'll see. Buildings can be done, but we have there the inertia. And in industry, you have different approaches. But what is very important, that there are big reports on it. And if you read all those reports, all of the industry decarbonization seems to have the same magic number in it. Things will be starting to take off by 2035. So let's start to work on things that we have to do, but we really have to look at back to the square one of communication 299. Do whatever you can do first in electrification and prepare for 2030 plus for the synthetic fuels. Thank you.
Thank you, Ronnie. We are running out of the time, but perhaps I would like to hear a comment from Jorgo and also put him a question that is brought by Roland Schulze. He asked about the policy instrument that could be controversial. Say basically you put a CO2 threshold for hydrogen production. So you just regulatory say you can produce hydrogen in the EU with such an environmental footprint. is it a way to go or it is not the way? Because Commission President says, well, that everybody would agree. We also want to make clean hydrogen the best choice in economic terms. So this everybody would agree. Jorgo.
Indeed, but we have two factors here. One factor, and Ronnie just elaborated on 2030 as being the time 2035 where big volumes will be used. But what about the immediate effect? We need also, and Case came up with that, an immediate effect right now. And that's the blue hydrogen that can only decarbonize until 60%. We need it because we can use this decarbonization fast and immediate in our strategy, but we want to avoid lock-in effects. That is why we can imagine an idea whereby you have for the next 10 years something like a premium for fast decarbonizers, but it's just a premium for 5 to 10 years, full stop. It's a sunset clause. And then the certificates that you give to clean hydrogen will be linked to a threshold of CO2, which is 90%, could be even higher. Case mentioned negative effects also using ATR, the autothermal method. And if you say, as of 2040, there will be no certificates anymore for any technology that does not reach more than 90% of decarbonization, that's a clear signal to the markets. It doesn't make sense to invest now into a technology which is not green or highly decarbonizing. And that is, I think, a method to really have a market incentivization for the right course. And I think everybody agrees. Christopher is one of the authors of this idea.
Thank you. Unfortunately, I need to close. There are some questions that I have not answered. So I would like to thank Barbara, Jorgo, Ronnie, and Kees for participating. And apologize that I was too optimistic about the timeline because I thought that, well, we will manage it. Well, 1.5 hours is already too long for the issues to be discussed. So I appreciate it very much. And thank you for all the participants at today's discussion. We will come back to hydrogen issues and we'll try to be very, very specific on some very, very short and narrow issues because trying to cover this broad subject is really extremely difficult. Thank you very much. And well, have a nice year and a nice day.
You're welcome.
Thanks all.
Bye.
Thanks for attending and thanks for organizing.
Thanks.
Have a good day.
Have a good day all.